Chapter 5, Reading Python Code, Part 2. This chapter covers repeating code the required number of times using loops, using indentation to tell Python which code goes together, building dictionaries to store pairs of associated values, setting up files to read and process data, using modules to work in new domains. In Chapter 4, we explored 5 Python features that you're going to see all the time as you continue in your programming journey. Functions, variables, conditionals, if statements, strings, and lists. You need to know those features to read code, and we explained why being able to read code is important whether or not we're using Copilot. We'll continue in this chapter with 5 more Python features, which will round out our top 10. As in Chapter 4, we'll do this through a combination of our own explanations from Copilot, and experimenting at the Python prompt. Section 5.1. Top 10 Programming Features You Need to Know, Part 2. This section details the next 5 of the top 10 programming features you need to know. Let's continue where we left off in the previous chapter with feature number 6, loops. Section 5.1.1. Number 6, loops. A loop allows the computer to repeat the same block of code as many times as needed. If a single one of our top 10 programming features exemplifies why computers are so useful for helping us get work done, it's this one. Without the ability to loop, our programs would generally execute in order, line by line. Sure, they could still call functions and use if statements to make decisions, but the amount of work a program does would be proportional to the amount of code we write. Not so with loops. A single loop can process thousands or millions of values with ease. There are 2 types of loops, for loops and while loops. Generally speaking, we use a for loop whenever we know how many times we need the loop to run, and we use a while loop when we don't. For example, in Chapter 3, our best word function, reproduced as listing 5.1, used a for loop because we know how many times we want the loop to run, once for each word in word list. But in getStrongPassword, which we'll see again in listing 5.4, we used a while loop because we have no idea how many bad passwords the user is going to type before they type a strong one. We'll start with for loops, and then move on to while loops.
Listing 5.1, best word function from Chapter 3.
A for loop allows us to access each value in a string or list. Let's try it with a string first.
See this code?
Notice that we don't need an assignment statement for char. That's because it's a special variable called a loop variable that's automatically managed by the for loop. Char stands for character, and it's an extremely popular name that people use for the loop variable. The char variable automatically gets assigned each character of the string. When talking about a loop, we often use the word iteration to refer to the code that executes each time through the loop. Here, for example, we would say that on the first iteration, char refers to v. On the second iteration, it refers to a, and so on. Notice also, just like for functions and if statements, we have indentation for the code that makes up the loop. We have only one line of code in the body of this loop, but just like for functions and if statements, we could have more. Let's see an example of a for loop on a list this time. Listing 5.2, demonstrating that we can process each value of a list like we process each value of a string. We'll also throw 2 lines of code into the loop instead of just 1, to demonstrate how that works too.
Listing 5.2, example using a for loop.
The code in listing 5.2 is just one way to loop through a list. The approach of for animal in list assigns the variable animal to the next value in the list each time through the loop. Alternatively, you could use an index to access each element of the list. To do that, we need to learn about the built-in range function. The range function gives you numbers within a range. We can provide a starting number and an ending number, and it will produce the range that goes from the starting number up to, but not including, the ending number. To see the numbers that range produces, we need to put the list function around it. Here's an example of using range.
See this code?
Notice that it starts with the value 3 and includes all values between 3 and 8. That is, it includes all numbers from the starting value 3 up to, but not including the ending value 9. Now, how is range going to help us write a loop? Well, rather than hard-coding numbers like 3 and 9 in the range, we can include the length of a string or list like this.
See this code?
Notice that the range values here are 0, 1, 2, 3. Which are the valid indices of our LST list. We can therefore use range to control a for loop and that will give us access to each valid index from the string or list. We can use range to perform the same task in listing 5.2. See listing 5.3 for the new code.
Listing 5.3. Loop example using for loop and range.
We've used a variable named index here, but you'll also often see people use just I for simplicity. That variable will be given the value 0 for the first iteration of the loop, 1 for the second, 2 for the third, and 3 for the last iteration. It stops at 3 because the length of the list is 4, and range stops 1 before that. Using indexing into the list, the code grabs the first element, then the second, then the third, and then the fourth, using the increasing indices. We could have also written the for loop without the 0. Range will assume we want the values between 0 and the value provided, like this.
See this code?
We'll stop here with for loops. But we're not done with loops yet because there's another type of loop that we need to talk about, the while loop. We use a while loop when we don't know how many times to loop. A nice example of this situation is in our getStrongPassword function from Chapter 3. We've reproduced that code here as listing 5.4.
Listing 5.4. GetStrongPassword function from Chapter 3.
We have no idea how many passwords the user is going to type until they type a strong one. Will it be on the first try, second try, or 50th try? Who knows? That's why we need a while loop. It ensures that the user is asked again and again until they provide a strong password. To write a while loop, we follow while with a Boolean condition. If it's true, Python runs one iteration of the loop. If, after that iteration, that Boolean condition is still true, then it runs another iteration. It keeps doing that until the condition is false, at which point the loop terminates. Now, we have enough information to make sense of the code for our getStrongPassword function. By looking at the code, we can see that it begins by using the input function to ask the user for a password. Then, there's a while loop. This loop continues as long as the password isn't a strong password. The Boolean condition not is. Strong password of password is equivalent to writing it as is strong password of password double equals false. To avoid an infinite loop and to ask the user to try again, we have another use of input inside of the loop. We need the call of input above the loop to get the first try from the user. Without that, the password variable wouldn't exist, and the while loop line would give an error because it wouldn't have a password value to pass to the isStrongPassword function. Don't forget that we can ask Copilot for an explanation of this code, using what we learned in Chapter 4, Section 4.2. This is useful whenever you're feeling that you aren't quite understanding what the code is doing or how it works. Here's the explanation we received from Copilot. This Python code defines a function named getStrongPassword. The purpose of this function is to interactively prompt the user to enter a password and keep asking until the user provides a password that is considered strong. The criteria for what constitutes a strong password is not defined in this function, but is determined by another function named isStrongPassword. The function begins by asking the user to enter a password using Python's built-in input function. The entered password is then stored in the variable password. Next, the function enters a while loop. The condition for this loop is not isStrongPassword of password. This means that the loop will continue to execute as long as the isStrongPassword function returns false when called with the current password. In other words, the loop will keep running until the user enters a password that is considered strong. Inside the loop, the function again prompts the user to enter a password. The new password replaces the previous one stored in the password variable. If this new password is still not strong, the loop will continue to prompt the user. Once the user enters a password that is considered strong, that is strong password of password returns true, the while loop condition becomes false, and the loop ends. The function then returns the strong password entered by the user. This function is a good example of using a while loop to repeatedly prompt the user for input until the input meets certain criteria. However, the actual criteria for a strong password are not defined in this function and would need to be implemented in the isStrongPassword function. This explanation is a very good description of the function and matches the description that we just gave. It contains useful general Python information as well, including a reminder in the final paragraph of why exactly we're using a while loop. The explanation also mentions that we need the isStrongPassword function to tell us whether a password is strong or not. We didn't highlight that function, which is why Copilot is telling us that we need to implement it. Copilot explanations can be wrong. We chose the previous Copilot explanation because it was the best answer from Copilot after we asked it to explain the code 3 times. One of the answers it gave us sounded quite plausible until it started talking about functions that didn't exist. We believe the explanations can be helpful as a learning aid if you run it multiple times and look for common ideas. But a principal goal of this chapter is to give you the tools you need to understand when it makes mistakes. We encourage you to use Copilot explanations going forward, and, if you're interested, ask Copilot to explain any code from prior chapters that you're still curious about. Again, these explanations can be wrong, so you should ask Copilot for several explanations to limit your reliance on a single erroneous explanation. As with anything related to AI coding assistants right now, they're going to mess up. But we've given the explanation here because we see this Copilot feature as a potentially powerful teaching resource now, and that will become even more true as Copilot improves. We're supposed to use a while loop in these kinds of situations where we don't know how many iterations there will be. But we can use a while loop even when we know how many iterations there are. For example, we can use a while loop to process the characters in a string or the values in a list. We sometimes see Copilot do this in the code that it generates, even though a for loop would have been a better choice. For example, we can use a while loop to process the animals in our earlier animals list, as in the following listing. It's more work, though.
Listing 5.5, loop example using a while loop.
Without the index plus equals 1, we would never increase the index through the string, and we'd print out the information for the first value over and over. That's called an infinite loop. If you think back to how we wrote for loops, you'll find that we didn't have to manually increase any index variables. For such reasons, many programmers prefer to use for loops when they can. We don't have to manually keep track of any index in a for loop, so we automatically avoid certain kinds of indexing problems and infinite loops. Section 5.1.2, Number 7, Indentation. Indentation is critical in Python code, because Python uses it to determine which lines of code go together. That's why, for example, we always indent all the lines of code inside a function, the various portions of an if statement, and the code for a for or while loop. It's not just nice formatting. If we get the indentation wrong, then we get the code wrong. For example, let's say that we want to ask the user for the current hour and then output some text based on whether it's morning, afternoon, or evening. If it's morning, we want to output good morning and have a nice day. If it's afternoon, we want to output good afternoon. If it's evening, we want to output good evening and have a good night. Take a look at the following code we've written and try to spot the problem with the indentation.
See this code.
The problem is the last line. It's not indented, but it should be. Because it's not indented, we'll output have a good night, regardless of which hour the user types in. We need to indent it so that it's part of the else portion of the if statement, ensuring that it only executes when it's evening. Whenever we write code, we need to use multiple levels of indentation to express which pieces of code are associated with functions, if statements, loops, and so on. For example, when we write a function header, we need to indent all the code associated with that function below the function header. Some languages use brackets, for example curly brackets, to show this, but Python just indents. If you're already in the body of a function, one indent, and write a loop, then you'll have to indent again, two indents, for the body of the loop, and so forth. Looking back at our functions from Chapter 3, we can see this in action. For example, in our larger function, reprinted as listing 5.6, the whole body of the function is indented, but there's further indentation on the if portion and the else portion of the if statement.
Listing 5.6, function to determine the larger of two values.
Next, consider our getStrongPassword function that we looked at in listing 5.4 earlier. As usual, everything in the function is indented, but there's further indentation for the body of the while loop. There are even more levels of indentation in the first version of our numPoints function, reproduced here from Chapter 3 as listing 5.7. That's because inside of the for loop through each character of the word, we have an if statement. Each piece of the if statement, as we've learned, needs to be indented, leading to the extra level of indentation.
Listing 5.7, numPoints function.
There's additional indentation in isStrongPassword too, reproduced from Chapter 3 as listing 5.8, but that's only to spread out one super long line of code across multiple lines. Notice that the lines end with backslash, which is the character that allows us to continue a line of code on the next line.
Listing 5.8 is strong password function.
Similarly, there's some further indentation in our second version of numPoints, reproduced from Chapter 3 as listing 5.9. But that's just to spread the dictionary out over multiple lines to make it more readable.
Listing 5.9, numPoints alternative solution.
Indentation makes a huge difference on what our programs ultimately do. For example, let's compare putting two consecutive loops versus nesting one in the other using indentation. Here are two loops in a row.
See this code?
That caused us to get the same output twice because we looped two separate times through the countries list. Now, if instead we nest the loops, this happens.
See this code?
We've used different variable names, country 1 and country 2, for each for loop, so that we can refer to both. On the first iteration of the country 1 loop, country 1 refers to Canada. On the first iteration of the country 2 loop, country 2 refers to Canada as well. That's why the first line of output is Canada, Canada. Did you expect the next line of output after that to be USA, USA? That isn't what happens. Instead, the country 2 loop moves on to its next iteration, but the country 1 loop doesn't move yet. The country 1 loop only moves ahead when the country 2 loop is complete. That's why we get Canada, USA and Canada, Japan before the country 1 loop finally moves on to its second iteration. When one loop is inside of another loop, this is called nested loops. In general, when there's nesting, the inner loop, for country 2 in countries, will complete all of its steps before the outer loop, for country 1 in countries, moves on to its next step, which, in turn, will restart the inner loop. If you see a loop nested inside another loop, chances are good that the loops are being used to process two-dimensional data. Two-dimensional data is organized into rows and columns of the kind you might see in a table, for example, Table 5.1. This kind of data is really common in computing because it includes basic spreadsheet data such as CSV files, images such as photos or a single frame of video or the computer screen. In Python, we can store two-dimensional data using a list where the values themselves are other lists. Each sublist in the overall list is one row of data, and each row has a value for each column. For example, say we had some data about the figure skating medals won at the 2018 Winter Olympics, as shown in Table 5.1.
Table 5.1, medals in the 2018 Winter Olympics.
We could store this as a list with one country per row.
See this code?
Notice that our list of lists is just storing the numeric values, and we can find a value in the list of lists by referring to its row and column. For example, Japan's gold medal corresponds to the row at index 2 and the column at index 0. We can use an index to get a complete row of data.
See this code?
If we do a for loop on this list, we get each complete row, one row at a time.
See this code?
If we want just a specific value from the medals list, not a whole row, we have to index twice.
See this code?
Suppose we want to loop through each value individually. To do that, we can use nested for loops. To help us keep track of exactly where we are, we'll use range for loops so that we can print out the current row and column numbers in addition to the values stored there. The outer loop will go through the rows, so we need to control it using range of len of medals. The inner loop will go through the columns. How many columns are there? Well, the number of columns is the number of values in one of the rows, so we can use range of len of medals 0 to control this loop. Each line of output will provide three numbers: the row coordinate, the column coordinate, and the value, number of medals, at that row and column. Here's the code and output.
See this code?
Notice how the row stays constant for the first three lines of output, during which the column varies from 0 to 2. That's how we work our way through the first row. Only then does the row increase to 1, at which point we complete the work for columns 0 to 2 on this new row. Nested loops give us a systematic way to loop through each value in a two-dimensional list. You'll see them frequently when dealing with two-dimensional data in general, such as images, board games, and spreadsheets. Section 5.1.3, number 8, Dictionaries. Remember that each value in Python has a specific type. There are a lot of different types because there are many kinds of values that we might want to use. We've talked about using numbers to work with numeric values, booleans to work with true or false values, strings to work with text, and lists to work with a sequence of other values such as numbers or strings. There's one more Python type that shows up often, and it's called a dictionary. When we talk about a dictionary in Python, we don't mean a list of words and their definitions. In Python, a dictionary is a useful way of storing data whenever you need to keep track of associations between data. For example, imagine that you wanted to know which words are used most often in your favorite book. You could use a dictionary to map each word to the number of times it's used. That dictionary would probably be huge, but a small version of such a dictionary might look like this.
See this code?
Each entry in the dictionary maps a word to its frequency. For example, we can tell from this dictionary that the word DNA shows up 11 times and that the word taxon shows up 13 times. The words here, DNA, acquire, taxon, etc., are referred to as keys, and the frequencies, 11, 11, 13, etc., are referred to as values. So, a dictionary maps each key to its value. We're not allowed to have duplicate keys, but as shown here with the 211 values, having duplicate values is no problem. We saw a dictionary in Chapter 2, listing 2.1, that stored each quarterback's name and their associated number of passing yards. In Chapter 3, we saw a dictionary again in our second solution for Noom points, reproduced earlier in listing 5.9. There, the dictionary mapped each letter to the number of points awarded for using that letter. Just like for strings and lists, dictionaries have methods that you can use to interact with them. Here are some methods operating on our Freak dictionary.
See this code?
You can also use the index notation to access the value for a given key.
See this code?
Dictionaries, like lists, are mutable. This means that we can change the keys and values in a dictionary, which is useful for modeling data that changes over time. We can use indexing to change a value. The value associated with morph is currently 41. Let's change it to 6.
See this code?
Our Freak dictionary allows us to start from whatever word we want and find its frequency. More generally, a dictionary allows us to go from key to value. However, it doesn't allow us to easily go in the opposite direction, from value to key. If we wanted to do that, we'd need to produce the opposite dictionary. For example, one whose keys are frequencies, and whose values are lists of words with those frequencies. That would enable us to answer questions such as the following. Which words have a frequency of exactly 5? Which words have the minimum or maximum frequency of all? As with strings and lists, we can use a loop to process the information in a dictionary as well. A for loop gives us the dictionary keys, and we can use indexing to get the associated value for each key.
See this code?
Section 5.1.4, Number 9, Files. It's often the case that we'll want to work with datasets that exist in files. For example, in Chapter 2, we worked with a file of NFL stats to determine the most effective quarterbacks. Using files is common for other data science tasks as well. For example, if you're plotting information about earthquakes around the world, or determining whether 2 books are written by the same author, you'll need to work with those datasets, and typically those datasets will be stored in files. In Chapter 2, we worked with a file called NFL_offensive_stats.csv. Make sure that this file is in your current program directory because we'll use that file now to further understand some of the code we used in Chapter 2. The first step in working with data from a file is to use Python's open function to open the file.
See this code?
You'll sometimes see Copilot add an R as a second argument here.
See this code?
But we don't need the R. The R just means that we want to read from the file, but that's the default anyway if we don't specify it. We've used an assignment statement to assign that open file to a variable named NFL file. Now, we can use NFL file to access the contents of the file. An open file is a Python type, just like numbers and strings and all of the other types you've seen to this point. As such, there are methods that we can call to interact with the file. One method is readLine, which gives us the next line of the file as a string. We'll use it now to get the first line of our open file, but don't worry about the line itself, because it's super long with tons of information about columns we won't end up using.
See this code?
It's not easy to pull individual values out of a messy string like that. So one of the first things we tend to do with such a line is split it up into its individual column data. We can do that using the string split method. That method takes a separator as an argument and splits the string into a list by using that separator.
See this code?
Now we can look at individual column names.
See this code?
That first line of the file that we're looking at isn't a real data line, it's just the header that tells us the name of each column. The next time we do read line, we get the first real line of data.
See this code.
Moving one line at a time like this is fine for exploring what's in a file, but eventually we'll probably want to process the whole thing. To do so, we can use a for loop on the file. It'll give us back one line on each iteration, which we can process in any way we like. Once we're finished with a file, we should call close on it.
See this code?
After closing, we aren't allowed to use the file anymore. Now that we've discussed how to read, process, and close a file, let's see a full example. In Listing 5.10, we provide a new version of our program from Chapter 2 that sorts quarterbacks by their total passing yards. In addition to showcasing files, we're also using many of the Python features that we've seen in Chapter 4 and the current chapter, including conditionals, strings, lists, loops, and dictionaries.
Listing 5.10. Alternative NFL statistics code without the CSV module.
That loop at the bottom, see this, has a lot going on. We explained this line in the annotations as looping through the quarterbacks from highest to lowest. The reverse equals true makes a sort from highest to lowest, rather than the default of lowest to highest. The key equals passing yards dot. Get focuses the sort on the number of passing yards, rather than, for example, the players' names. If you'd like to break down this line of code further, feel free to ask Copilot for further explanation. This highlights the balancing act that we're trying to maintain here. To know enough to be able to get the gist of code without necessarily needing to understand every nuance. This program works just fine. If you run it, you would see the same output as if you ran the code from Chapter 2. Sometimes, though, it's possible to write a program more easily using modules. We cover modules in more depth in the next section. And that's what the program from Chapter 2 did. Because CSV files are so common, Python comes with a module to make it easier to process them. In Chapter 2, the solution that we were given used the CSV module. So, let's discuss the main differences between our code in Listing 5.10 that doesn't use the module and our code from Chapter 2, reprinted here in the following listing. Our prompts given to Copilot aren't shown.
Listing 5.11. NFL statistics code using the CSV module.
First, Listing 5.11 uses the CSV module to make dealing with CSV files easier. The CSV module knows how to manipulate CSV files, so, for example, we don't have to worry about breaking a line into its columns. Second, Listing 5.11 uses the with keyword, which results in the file automatically being closed when the program is done with it. Third, Listing 5.11 reads the entire file first before doing any processing. By contrast, in Listing 5.10, we read and process each line as soon as we read it. More than one way to solve a programming problem. There are always many different programs that can be written to solve the same task. Some may be easier to read than others. The most important criterion for code is that it does the correct thing. After that, we care most about readability and efficiency. So, if you find yourself struggling to understand how some code works, it may be worth some time looking at other code from Copilot, in case there's a simpler or more understandable solution available there. Files are used commonly in computing tasks because they are a common source of data to be processed. This includes CSV files like the one from this section, log files that keep track of events on computers or websites, and files that store data for graphics you might see in video games, among others. Because files are so commonly used, it's no surprise there are many modules that help us read various file formats. That leads us to the larger topic of modules. Section 5.1.5. Number 10. Modules. People use Python to make all kinds of things. Games, websites, and apps for analyzing data, automating repetitive tasks, controlling robots, you name it. You might be wondering how Python can possibly let you create so many different types of programs. Surely the creators of Python couldn't have anticipated or created all the needed support. The truth is that by default, your Python program has access only to some core Python features, such as those we've showed you in the previous and current chapter. To get any more than that, we need to use modules, and to use a module, you need to import it. Modules in Python. A module is a collection of code designed for a specific purpose. Recall that we don't need to know how a function works to use it. It's the same with modules. We don't need to know how modules work to be able to use them, much as we don't need to know how a light switch works internally to use it. As users of modules, we just need to know what a module will help us do, and how to write the code to correctly call its functions. Of course, Copilot can help us write that kind of code. Some modules come with Python when you install it, but we still need to import them. Other modules we first have to install before we can import them. Trust us, if there's a specific kind of task you want to do with Python, someone's probably already written a module to help you out. You might be wondering how to determine which Python modules you should use. How do you know which ones exist? A simple chat with Copilot or Google search is often helpful. For example, if we Google Python module to create a zip file, the first result tells us that the module we need is part of the Python standard library, which means that it comes with Python. If we Google Python module for visualization, we learn about modules named Matplotlib, Plotly, Seaborn, and more. Searching for each of these should lead you to galleries of visualizations showing you their capabilities and what each is typically used for. Most modules are free to download and use, although your search results can help you confirm whether a module is free and its specific usage license. We're going to hold off on installing and using newly installed modules until Chapter 9, but, at that time, you'll see this process of finding, installing, and using relevant modules to help us complete our tasks. Table 5.2 has a list of some of the commonly used Python modules and whether they are built in or not. If a module is built in, you can import the module and start using it right away. If not, you need to install it first.
Table 5.2, Summary of commonly used Python modules.
In Chapter 2, our code used the CSV module that comes with Python. Let's continue here by learning about a different module that comes with Python. When people want to organize their files, perhaps prior to backing them up or uploading them, they often archive them first into a zip file. Then they can pass around that single zip file rather than potentially hundreds or thousands of individual files. Python comes with a module called ZipFile that can help you create a zip file. To try this, create a few files in your programming directory and make them all end with CSV. You could start with your NFL offensive stats.csv file and then add a few more. For example, you could add one called actors.csv with the names of a few actors and their ages, such as.
See this?
And you could add one called chores.csv with a list of chores and whether you've finished each one.
See this?
The contents don't matter as long as you have a few CSV files to test with. Now we can use the ZipFile module to add them all to a new zip file.
See this code?
If you run that code, you'll find a new file called my_stuff.zip that contains your 3 CSV files. Working with zip files directly used to be a very specialized, error-prone task with other earlier programming languages. But that's not so with Python. Python comes with modules that are helpful for data science, making games, dealing with various file formats, and so on. But again, Python can't come with everything. When we need more, we turn to downloadable modules, as we'll see in Chapter 9. In this chapter, we introduced you to the second half of our top 10 Python features, as summarized in Table 5.3. We've covered a lot about reading code in the previous chapter and this chapter. Although we haven't covered everything you might see Copilot produce, you're in a good position to spot-check Copilot code to determine whether it's given a good attempt at producing the code you requested. We also showed more examples of using the Copilot explanation tool to help you understand new code. In the next chapters, we'll see how to test the code from Copilot to determine whether it's correct and what you can do when it's not.
Table 5.3, Summary of Python code features from this chapter.